So the next sum that we'll be considering is we'll have to prove whether a defined binary operation is commutative or not, and associative or not. So we need to, here in this sum, they have defined the binary operation as a star b equals a raised to the power b, and I need to show that this operation is neither commutative nor associative. Now, essentially, what I need to first do is I skip the portion where I define or whether I analyze that the given star operation is a binary operation or not. That's easy if you get higher marks in examination. So you get this sum for 5 marks or 6 marks. You can essentially do that portion as well. That is, you analyze whether this operation is binary operation or not. That will be easy because, of course, z, that is the set of positive integers. So that's z plus, is a non-empty set. And for any two positive integers, obviously a raised to the power b will also be a positive integer. So that's very obvious, and it's an easy way to prove the binary operation. So we skip that portion and we move on to the core of the sum, and we need to find out whether this binary operation is commutative or not, and whether it is associative or not. So as I've mentioned before, in order to disprove a statement, it's sufficient to take one particular example where that given situation does not hold. So here again, since I have been asked to say that the binary operation is neither commutative nor associative, it's obvious that they want us to disprove this statement. That is, they want us to give a particular example where binary operation cannot be called a commutative, and another example where binary operation cannot be called associative. So that's this is the easier part of the sum. This is a hint for the sum essentially. So what I do is I take 3 elements, 3, 4, and 2. You could have I could have taken 2 before because 2 comes before 3, but what I'll be doing is I'll be using these 2 numbers first, and then I'll be using 2. So I put 2 at the later portion. So I have taken 3 elements, 3, which is a positive integer, undoubtedly. 4 is also a positive integer, and last but not the least, 2 is also a positive integer. So what I do is I formulate the operation or the setup based on the definition of the binary operation. So they had defined that a star b is a raised to the power b. So I say that if a is 3 and if b is 4, then a star b will be 3 to the power 4, because 3a is 3 and b is 4. So 3 star 4 is 3 to the power 4. But if I reverse, that is, if I take a equals 4 and b equals 3, then 4 to the power 3 is 4, 4 star 3 is 4 to the power 3. Now the commutative law stated that a, let's call this star itself. So the commutative law holds when we can say that a star b equals b star a. So that was the statement for the satisfaction of the commutative law. Now here, of course, you can see that a star b is not the same as b star a. So here, instead of taking it b star a, let me just write it b a. So that way we'll be able to prove the commutative law in a more systematic form. So I have assumed at the beginning of the sum that a is 3 and b is 4. So that I have done before I start with the analysis of commutative law. That is meant to be 4. That doesn't look like 4. Yeah. So at the beginning of the sum, I have defined that a is 3 and b is 4. So a star b becomes 3 star 4, which is 3 to the power 4. And by the same assumption of a equal to 3 and b equal to 4, if I define b star a, it turns out to be 4 star 3, which is 4 raised to the power 3. So if I define a star b, the resultant, and if I define b star a, the resultant, these two numbers are undoubtedly different. So if these two numbers, that is, take this equation as one equation and take this equation as another equation. Let me just underline this equation and this equation. If the right hand side of these two equations is different, it essentially means that the left hand side of these two equations is also different. So 3 star 4 is not the same as 4 star 3. Which means I essentially find out an example or the value of a and b for which this statement, the fact that a star b equals b star a, does not hold. which means 3 star 4 is not the same as 4 star 3, or A star B is not the same as B star A for all AB. So that essentially is the root cause of problem. A star B needs to be equal to B star A for all values of A and B under the set of considered set. So here what happens is I can say that star is not a commutative operation, because this A star B equal to B star A does not hold for all values of A and B. I have a value of A and B in the set under consideration for which this A star B equal to B star A does not hold. So that proves that my given binary operation essentially is not commutative. Essentially, not all binary operations need to be commutative. There can be binary operations which are not commutative. So the next part that we move on to is the associative law. And by associative law, it said that A star B, putting in bracket, star C, pardon my terrible handwriting, A star B star C should be the same as A star, bracket open, B star C, for again for all values of A and B. So let me just write for all A, B, C belonging to whichever set you are considering. So since we have considered here the set of positive integers, this will be the set of positive integers. So that was the definition of associative law. Now what we here do is, this portion is done, so we move on to this portion. This is the associative law. So what we do is, as I had mentioned before, I'll be using 3 and 4 for the first part of the sum, and then I'll be using all 3 of the numbers, because commutative law requires 2 elements and associative law requires 3 elements. So we take 2, 3 and 4. So here, as I have defined, I have taken A to be 2. So this is A, this is B, and this is C. So I have defined A to be 2, B to be 3, and C to be 4. So when I say A star B star C, it essentially means take it step by step, take it one notch at a time. 2 star 3 is A raised 2 raised to the power 3, because A star B is A raised to the power B. So 2 star 3 is 2 raised to the power 3. So that will be this portion. Then you take this element as a single element. So you take this as some other element, and then you say this entire element star 4, which means this entire element raised to the power 4, because you have the first number. What you do is you take the first number and then you raise it to the second number. So in this case, you will have the first number as 2 to the power 3, the second number as 4. So that means it will be 2 to the power 3 raised to the power 4. So that will be 2 to the power 3 raised to the power 4. That will be this portion. This will be my first equation. So for this equation, which is A star B star C, that is this portion, I have 2 to the power 3 to the power 4. In the next equation, this time I take this portion. So what I do is I try to find out whether this equation holds. So I take the left hand side. So this is the left hand side. And then I take the right hand side. So for the right hand side, I have 2 to the power, again, take it at one step at a time, one notch at a time, 3 raised to the power 4. So that will be 3 raised to the power 4. Then it's 2 star 3 star 4. So it's 2 star 3 raised to the power 4, which means it's 2 raised to the power 3 raised to the power 4, which means the difference is the bracketed portion needs to be in a single bracket. So it's 2 to the power 3 and that entire number is raised to the power 4. But here it's first I raise 3 to the power 4 and then I raise 2 to that number. So 3 to the power 4 is 3 times 3 times 3 times 3, so that's 9 times 9 square, 9 9s are 81. So this is 2 raised to the power 81. This is 2 raised to, if you know the exponential law, that will be 2 raised to the power 3 to the power 4, that will be 2 raised to the power 4, 12. So that's 2 raised to the power 12. Let me just remove this. Yeah, so this is 2 raised to the power 12 and this is 2 raised to the power 21. Undoubtedly these two are not the same. So what I see is 2 star 3 star 4 is not the same as 2 star 3 star 4. So this does not hold for all values of ABC belonging to the set of positive integers under consideration. So again, we find out a particular value of ABC for which the given situation does not hold, which essentially means that my definition of my binary operation under consideration is not associative.